Yeah, it's my pleasure to welcome you to our 5th workshop in the series of the Open Modeling Foundation workshop series. Yeah, from the certification working group. So it's all around modeling. We have different topics. We have a total like 7 workshops. Today it's about research computing. It's our honor to have Christine Kirpatrick and Paul Brenner here. So the goal of the workshops is, on the one hand side, really to have experts who have discussions, give talks, and then also really be interactive a lot with the audience. And then I directly lost now a participant. Um, and so we will talk and we will put all the workshops together in a paper with all the outcomes, the discussions, so everyone who's interested to contribute to that will be informed about this. And with that, I start to share my screen with a short introduction to the topic. And of course, it does not want to share. Do you see this?
Yes, we can see it.
Great.
With the sidebar.
Yeah, I will. So we talk today about research computing and modeling. And I make it fast, but because the panel discussion includes some concepts, I bring some concept up. So research computing. So this, you being here, you're probably, interested in the research computing and modeling part. And so what is the definition of research computing? There are a lot of different definitions, and we come probably to that in the panel discussion. But so what does it mean to be in research computing? So there's increased complexity of today's research questions. We can answer nowadays questions we couldn't even ask 10 years ago or 20 years ago. We have really complex data, hardware and software, and the skills required to work with them. We have a greater need for openness and reproducibility, and also a lot of interdisciplinary distributed projects. Like, we work worldwide or in big teams together to address challenges. And it's also, we want a better workforce preparation. And how can models support this? Because modeling is part of this. And if you look at the research computing landscape, you have the lab instruments, you have web-based agile methods, you have the data compute intensive problems, you have research software, distributed computing and data and high-speed networks. In the middle is a researcher, a little bit sad-looking researcher, like all this, what all the components they have to deal with. And there's a need for support via models, for example, that could help them to make them happy researchers. And so if we look at usability, for example, so usability came up in some of our workshops about also modeling, about, other publications and modeling. So and usability really just means that making sure that something works well. That is how we talk about usability here, so that it's really used for the intended purpose. And I really like this one. A user interface is like a joke. If you have to explain it, it's not that good. And reproducibility, I think we all know, reproducibility crisis. But what does it really mean? And there are a lot of different definitions out there. But it really means, so the definition we use here is obtaining consistent computational results using the same input data, computational steps, methods, code, and conditions of analysis. And I think quite a few probably in academia have seen the situation. Don't worry, you don't have to start your code from scratch. You can reuse software that the previous person on the project wrote several years ago. Are there instructions how to use it? I doubt it. Is the code commented? Not likely. Where are the files? Who knows? This is gonna to be painful, isn't it? Just a scratch. So I think, a typical situation in reproducibility. And when we talk about interoperability, I like the definition that it's really the ability of two or more systems or components to exchange information and to use information that has been exchanged, so that that the bridges are connected, not like in the picture. And with that is also, so ComSys is one of the model libraries which are really also used in research computing for different purposes, and it's a library of several different models. And we have also a ComSys talk in this workshop series, but just pointing to it, there are models also for research computing. And with that, we will come in a moment to our experts. So Christine Kirkpatrick, and sorry for the typo there in the slide. She's from the San Diego Supercomputer Center. She's the director for the data services there. She leads a couple of projects as a PI. So, for example, Research Coordination Network for FAIR in ML, and I blank on the other one at the moment, but I let her then introduce herself. And Paul Brenner, a former colleague of mine at the University of Notre Dame, he's the director of the Center for Research Computing, and he is in the US Air Force Reserve, so he has quite a few projects also with NSF, NIH, I think DOE and DoD. And with that, I stop sharing my screen. And I let Christine start with a story from the trenches.
Sure. Thanks so much, Sandra. And hopefully you can hear me okay. Okay, thank you. Yeah, so you mentioned a few projects that I'm involved in. I'm also Secretary General of the International Science Council's Committee on Data, and involved in a couple National Academies committees related to data, especially the Board on Research Data Information and the U.S. National Committee on Data. And then I also had the GoFair US office. So I'm very involved in data, but my background's actually in infrastructure and software before that. And so that's where our research data services group tries to bring everything together to layer in those things that are needed to support data-driven projects, but also provide kind of the meat and potatoes, if you will, that surrounds the HVC systems. I think this is a really interesting topic. I think that, it can be difficult for people who largely come from the infrastructure side of delivering research computing to think in terms of models. Another word I like to use, I think, in this context would be patterns, of trying to define similar ways of doing things, and almost templating out how you can approach different things, whether it's from the architecture side or even what you might call a workflow. And so maybe with that, I'll let Paul introduce himself.
Yeah, thanks, Christine. So I'm Paul Brenner. I'm a director in the Notre Dame Center for Research Computing, also a professor and principal investigator on a number of awards across the Department of Defense and National Science Foundation, DOE. Also happened to be a cyber officer in the Air Force Reserve. So spent a lot of time thinking about computational infrastructure and data in terms of trust and responsible sort of use, such that the discoveries we make, whether we're doing sort of open source and sharing those with society, or the mission critical systems that we deploy, can be trusted in their time of need. So I think a lot of shared modeling helps us establish that shared trust and that shared understanding. And it's important as we think about what degrees of open, we want to be responsible and respectful for people's, hard work and intellectual property. But at the same time, we need to establish baselines so that we can not only collaborate more efficiently, but collaborate with a level of understanding that leads us to have trust in the discoveries we're making and the systems that we're building. So happy to talk about that broadly in research computing through all the layers, from sort of at the top, at the output coming out of the systems that we're using, to the software we're designing, to the middleware and the orchestration that moves us across the systems to the operating systems firmware, and then ultimately to a lot of the sort of novel hardware. We've seen a resurgence in novel hardware, especially as we look at the AI ML sort of race that's going on right now. And so thinking about hardware all the way up to user interface, and again, with the goal of making sure that we can trust and understand the discoveries and the systems we're building. So happy to have this discussion.
Thank you so much, both. So yeah, with the first, then, so one story where you said, oh, this was a real challenge to work with that, with, so Christine, one example story. I know you have probably dozens of examples, but
Well, I guess, maybe to betray the way I come at things, is my master's is in a really long title that just means systems of systems engineering, and basically a trained enterprise architect. And the way, I guess, my religion is systems of systems, and looking at the intersections and interfaces of those systems rather than trying to concentrate on every specific thing within the box, which is also important. But a lot of the legacy IT systems and research computing are not architected that way. They can often be built as monoliths that people think, I'm going to put this in and it's going to be here forever. Hopefully none of my colleagues will mind me dissing. One of our difficult systems to replace had been the Oracle directory services that were basically everything was tied to that as a piece of legacy. And that was, holding up our namespace for canonical names, and making it difficult for a lot of systems to upgrade. We even have people who have been in our center for more than 15 years who can't get their name, their what would be their logical canonical name as a login because of what's been in this database for dozens of years. And so I think it's very important to think about implementing standards, not implementing proprietary systems, because you can be tied to them for longer than you can even find people who have the expertise to administer them. And then it becomes just a huge undertaking to try and disconnect them from all the systems that rely on them. So I'm lucky in my division, we're not using this anymore, but there are still a few places that are still using this old system. And the groups that rely on it have had to take in the maintenance of this incredibly decrepit old system. So it's not over yet. It's a horror story that's ongoing.
Yeah, absolutely. Yeah, I think I can relate to situations like that. And Paul, your example story around a challenge.
Yeah, sure. And I completely agree with Christine on the importance of systems. So the one I'll share, and also sort of balance it back to how this may change reproducibility, to having an open model such that we understand how to reproduce, the discoveries of maybe a prior grad student, but also a prior generation. So I think generationally, when some of our old systems that we're retiring, and I'll specifically reflect on the AFS file system, the Andrew file system, which had many decades of outstanding and sort of innovative use, and has still remained some really unique properties that have been helpful for our scientists. But at the same time, technology continues to evolve non-linearly. And so we've had many changes in sort of file system and data orchestration over the years. And now we're to the point, well, some of our faculty still leverage it for their workflows, that are specific to how they've segmented and built their specific orchestration of work. We have other faculty and students that then try to run it on newer file systems and discover that when they were transferring files, the entire file did not move because the file systems were not interfaced in the same way. The way they handle low-level things is with respect to maybe even like a file pointer or something like that, and you don't get a full transfer, which is absolutely, critical to make sure you had all of the initial data, whether you're in machine learning or you're training, or these were initial, input files for trajectories for molecular dynamics. So to think that file systems and moving data between them, is that a part of an open model? Is that part of, it really is towards making sure you can be reproducible. So they may have shared the software code for the open model, but they can't reproduce the science because the infrastructure has also changed. So that description of the open model also at least has to have some sort of sort of an open or a cataloging of some of the architecture so that for full reproducibility, they can reach that. And it's not in every occasion, but without some level of control or understanding of what those underlying feature differences, and this being an example of file system differences over the decades, you don't know which of your key simulations or your key sort of systems you're building are going to run into these problems. So I think it's really important when we think about the open model to at least catalog and document some of that infrastructure. A goal would be to make each layer and abstraction of the infrastructure sort of independent. I don't think we're perfectly there, but we need to keep thinking about that as we design systems moving forward.
Absolutely. So Ishmael did put a URL to the notes document. There are also 10 questions, and I start with the first questions to our panelists, but if you have directly a question you would like to discuss with us, please put something in chat in the notes, raise your hand. We are happy to discuss questions you would like to see discussed here. So let me start with the first one. And this is a tough one because it's also different for every researcher. But what do you think are the key challenges researchers face in terms of computing resources and modeling tools in their respective fields? And how can these challenges be addressed, by us as a research computing and modeling community? So this time I might start with Paul and then Christine. We switch around.
Yeah, sure. So we've actually started integrating some design thinking methodology into trying to really capture what our users, graduate students and faculty and undergraduates need for their particular workflow. I think it's important to start putting ourselves in their mind. Over the years, I think we've all said, okay, as engineers, we often tend to gather the requirements and build the system as efficiently as possible within the limited budgets. And that cycle works, but over time, you start to lose sort of the user experience broadly, and that that leads to designing systems that actually may not necessarily fit the user need. So in that, specifically over the past couple of years, we've been starting to understand different groups. So when you ask what are the key sort of needs of the researchers, right? Our first is, okay, which sort of researcher are you? Are you coming in with 20 years of experience and you're going to bring in your postdocs and all of the rest of your graduate students and a couple of research programmers? Are you that sort of level of portfolio? And at that level, the researchers I really feel need support in larger infrastructure, in terms of making sure that the infrastructure we're providing across is complete and robust, and the performance levels they need, right? Because I would consider them our expert sort of high performance user base. But at the same time, especially, I wouldn't just say at a university, because I spend a lot of time talking with those in the government and in commercial sectors, and there's always a new user, right? If we're going to grow the community, if we're going to grow the capabilities, then you should always want to have new users, folks that you're going to have to sort of help in that front end. And I think the challenges for those researchers are a paradigm shift, right? So a shift from a laptop with sort of laptop-centric operating systems and files and compute capabilities to really thinking in the shift to a distributed systems thinking. And so that takes some training, that takes some, sort of hand holding in terms of understanding where your data has just flown, right, is no longer on your laptop, what that means in a system that is a system of systems that's connected far beyond the laptop. So we spend a lot of time helping our sort of new folks who may be absolute experts in their domain, but their domain has existed traditionally on a laptop, and to how we use complex research computing infrastructure and really helping them through that journey of transition. Certainly, there's a lot of additional sort of what we call user profiles that we've been looking at in the design thinking process. But I think in the big picture, sort of our advanced users with a larger skill set, it's really deploying in high performance systems and helping them, tweak as much they can out of those specific systems. And for those that are new, we're really helping them on the journey beyond the laptop. Ultimately, we do have some that we meet, which their journey would be a powerful workstation. And we say, look, you don't need large research computing infrastructure. That is maybe an inertial climb that right now is not necessary. And they're always sort of surprised when we say, for you, a powerful workstation might do the job. But helping them through that journey and understanding what those levels and the complexity that comes with it. So those are the two very common things that we see. And certainly we can talk more about specific, personas in the user base.
Thank you so much, Paul. Christine?
Yeah, I'll just compliment what Paul said. I think, just in some regard, the challenges can vary from research domain to research domain, because you certainly have some research domains where the average user, if you will, has maybe more advanced skills in regard to research computing, and the tools are perhaps a bit better. But even so, I think one thing that kind of unifies all domains is the unevenness, the haphazardness with which people get trained on those tools in their domain, however good or poor they are. And so I think this is a place where there are already some decent models. The carpentries comes to mind, both software, data, library carpentry, kind of coming at things from a more systematic way, providing just-in-time, online learning modules, and not assuming that people know anything, having all the instructions for how to install and begin to operate in these environments would be helpful. And then, of course, easy to use interfaces at all times. And the less that people have to assemble themselves is always the better.
Great, thank you so much, both. And just a reminder, if someone else has a question, otherwise we discuss the prepared questions. So could you elaborate in the role of research software engineers and science gateways in supporting researchers and utilizing computational resources and modeling tools effectively, really from that point of view? So science gateways, maybe I should ask, does everyone on the call know what science gateways are? Or is there a short intro to science gateways would be good, an explanation? You can just raise the hand if you would like an explanation. Okay. Ishmael. I like it. So science gateways are a concept really that describes end-to-end solutions for research domains. And that means really connecting from user interfaces to different research computing infrastructures or data infrastructures or lab instruments, and providing a community with a, let's say, virtual research environment or dashboard that is really tailored to them, and that can hide as much as desired from the complex infrastructure and make it easier for them, that they don't have to become acquainted with the nitty-gritty details of, all the research infrastructure, like research computing, high performance computing, maybe they're in the cloud. Researchers often want to focus on the research questions and not have to, know like, oh, I have to log in this and here and the other, and to get this data, I have to go there. So science gateways help with these complex situations to make it easier to access all these different infrastructures. And research software engineers are people who are developing software in research projects, to make it this definition very short. Yes. So with that, Christine, to look from the perspective of Science Gateway or research software engineers on the challenges.
Yeah, well, you really lined it up nicely for me, Sandra, so it makes it easy. But I think it's just not possible or efficient for researchers to replicate the logic and functionality that you can bake into a gateway. Here's an easy example, not a gateway. We have a birthday party for my dad's 75th birthday this weekend. Someone said, can we make coloring book pages for the kids? And so I opened up an application that knows how to do the 10 steps to take a photo to something that looks like a really bad photocopy, AKA line art. It's the same steps, no matter what photo you have. It would make no sense for me to be trained in Photoshop to go through all these steps. The outcome would be completely similar. But we're doing the same thing over and over across the entire world, where researchers are having to get to know all of these things that don't add to the science, that don't add to human knowledge, and really just waste the time of people with good brains. And time is our most precious resource. So anytime you can bake something like that into a gateway, I think it's really important work that advances science in a critical way because it saves time. I also think Paul touched on some of these points, that RSCs are critical because they give us kind of the recipes for how are we doing those things, so that we can replicate our own research, and that we can see the processes in a transparent way so that they're documented and reproducible.
Great, thank you so much, Paul.
Yeah, I think from a open modeling, I think I'll start with the RSCs, and I'll talk to the science gateways. I think that certainly everyone that I've ever worked with that has written a piece of software tends to hope that that software will be reused. And the reality is the majority of it will not be. And there's a number of reasons for that. You need a community around, supported software. You need expertise and modularity of the software. And all of these additional requirements is very hard for that individual graduate student or that undergraduate to ultimately see to realization. And so partnering the researcher, whether that be the grad student or the undergrad or the postdoc, with a RSC who can help with those harder, is there a community out there? How can I connect you to a community that may be leveraging this software? Can I help you design the software so that it will be modular, so that it may tie into additional platforms, so that their vision of reusable code can actually grow? Can I even the basics we find so often, can I teach you how to get your code into a repository and version control your code, so that if someone else were to want to add on to your code or revisions to your code or in parallel to fork your code, those sort of concepts may not be immediately apparent to an expert in a particular domain, chemistry, biology, theology. And so I think the RSE really provides that bridge to what they really were hopeful for anyway in their discovery. They want to share the discoveries. And if they were contributing to code, they want those codes to go in that other people will use and reproduce. So I think a lot have that same vision. The researchers want to make discoveries that will be reused, reproduced, but they may not have necessarily the skill set in terms of the cyber infrastructure. And the RSCs provide that bridge to sort of helping that realization of seeing the reuse of that particular code and really the reproduce of those algorithms and the things that the individual researchers were trying to discover. And so I think then the evolution of that is not only in the code base where the RSCs can help make that happen, but then eventually, into more mature platforms where there is, as Christine mentioned, there's a large user set that doesn't need to reproduce or re-engineer this sort of specific feature set over and over, whether that be this image editing or whether that be, editing of a specific, DNA strand in a sort of in a bioinformatics aspect. So wherever we can eventually get to say, look, not only have we made the code reusable, but in fact, the process itself can be made, more accessible to more researchers through a scientific gateway, right? And again, I really try and think about, okay, the majority of our researchers have now through the evolution started with a laptop, somewhere in their, K through 12, right? And so that is where they become centric. In fact, we could say even now it's a phone. I don't know that we're always necessarily bridging to research on the phone, but I'm surprised as a researcher how often my students will go ahead and just start something on their phone. Can I get to it from my phone? So a scientific gateway acts as sort of a bridge, right? As they think about how from my laptop do I get to this feature set? Do I get to this scientific algorithm? Do I get to data? And so the RSE may have helped them get their code into their platform, but at some point they may not even need to write the code in the first place, right? And they can go to a platform, they can go to a scientific gateway where the code, the algorithm is already there, and they can really focus on the bioinformatics or the natural language processing or whatever they were looking for as that particular tool. And they may get to it from their laptop, and they might even be able to get to it from their phone. And that's pretty exciting.
Yes, very cool. So did this also answer the questions about science gateways, what science gateways are, what RSEs do? Otherwise, please jump in, ask your question. I have one. Yeah, we have further questions for the panelists. So how do you see the landscape of research computing evolving in the next 5 to 10 years? I know that is tough, particularly with the advancements like in cloud computing, machine learning. Just to mention ChatGPT nowadays, we have to mention ChatGPT always now, and big data analytics. So yeah, we switched the order again, and this time we start with Paul and then Christine.
Sure. I think a lot of us that are in technology get really excited about new technologies, and I'm glad we do, right? This is our community. But I think sometimes we also have to recognize the long tail and some of the other realities come in, right? So 5 years ago, someone would have said every research computing facility really will be in the cloud, and all your engineers will need to learn to have all of this running and orchestrated on cloud resources. I don't know that that's necessarily come to reality. It takes a while to orchestrate those sorts of things. There are issues with cloud still being tied to individual vendors. There's not the level of sort of mobility across cloud platforms. There are certainly tools that can help you do that. But I don't know that we've all suddenly developed our engineers into cloud engineers and our software to be, truly cloud centric with serverless computing and all these other paradigms that have been sort of proposed within the cloud. So I think we have to be a little careful when we say 5 years out, sort of over, will machine learning continue to be, I believe a growing part of the research portfolio? Yes. Will everything become solely machine learning on data? I don't necessarily know. I don't think, fundamental simulation is going away for, testing and evaluation of, theory. So as we move forward, I think we'll have to think about architectures that have to support. Unfortunately, we continue to add. I don't see a lot going away at the moment. I think we'll have to add in not only what I would call hybrid, where our infrastructure is both local and in cloud, and we'll need to move from clouds. We'll also have to think of, certainly more data-centric infrastructure. I think we've been talking about it for 20 years, but only in the past 5 has the data and the machine learning, the data availability and the machine learning capabilities gotten to the point where I think there is a significant shift in the percentage of time that our scientists will spend doing machine learning on various data sets, more so than simulation on fundamental theories. So our file systems, I'll share another horror story without calling out a specific vendor. But one of our fairly young file systems was optimized for high performance computing, which is you have thousands and thousands of cores writing to a small number of files, but you want high capability of the file system to be able to take concurrent writes from thousands of cores, which is non-trivial. The file system did a good job at that. Within the past 2 years, the file system has been crippled and inaccessible for weeks because the growth of machine learning. And in machine learning, the file system access is very different. We have millions and billions of files. that maybe just a single machine with a number of GPUs is trying to read through over and over and over as a retraining process. So we went from thousands of cores writing to a small number of files to maybe a single machine or a couple of GPUs touching billions of files and mostly read access. Totally separate, totally redesigned, rethinking the infrastructure, which has been a challenge for us. So I think to answer your question of where we're going forward, I don't know that we'll be able to leave any of the particular capabilities. We're still going to have HPC. We're still going to have to support the fundamental simulation. But at the same time, we will have to have systems that are sort of supporting heavy read for data-centric sort of machine learning applications. I think, we will have additional, right now, NVIDIA is king in GPU architecture, but, competitive markets will eventually bring more architectures onto our data center floors that will allow for training, these various transformer-based neural nets, and new algorithms will certainly supersede those. So I think we're going to have more over the next 5 years architectures. I don't see a reduction in the architectures. That's not always great news for our engineers, and it's hard for reproducibility, but I think we are looking over the next 5 years at a challenge of we will have. You want to make your model sort of open and reproducible, but the underlying software stack will be actually more diverse. The architecture will be more diverse. The orchestration will be more diverse. So I think it will be harder than easier moving forward. But I think that's why we just have to keep a focus on reproducibility and open models as we go through this challenging sort of time of more architectures, and whether that be hardware or software, than we had before over the next 5 years.
Thank you so much, Christine.
Yeah, I completely agree with everything Paul said and found that really insightful. I stuck a little bit closer to 5 years because if I knew what it would be like in 10 years, I would go work in industry and make millions of dollars. But I mean, I guess actually the long arc of my career shows exactly what Paul said, is that some people, move at lightning speed, and the rest of us are dealing with the long tail for a long time. So I could say a lot of the things we have now will still be here in 5 to 10 years. But maybe if I could, build on some of the topics we've already talked about. Commercial cloud. So if you're using commercial cloud and where a lot of these AI tools are, it's really pushing on people to tool up their software skills, less so than infrastructure skills in the past, at least as far as research computing groups go. However, our on-prem environments have not gone away. One would have thought you would sound like a lunatic to say that you needed an on-prem cloud. We still have them at SDSC. We still have outside customers and research partners who need them and have specific use cases. And so I think we're still going to need people who know how to build these things and how to interoperate the software stack with the underlying infrastructure and how to architect these out. And that, I would say, is even more the case in Europe, where there are a lot of other regulatory drivers that keep things into on-premise open source stacks. But that leads me to maybe my main focus, and this is just something that I've been really ruminating on recently, is how few people there are in research computing that really understand the whole stack. I think it's, well, and I can stop and take, is it Juan's question, or because before I move to the next point.
Yeah. Sang, you would like to?
Yeah, I can ask after Christine you finish properly, because I actually I have a question from last topic on the gateway.
Okay. So just to close out that idea of needing to understand the whole stack, if you hadn't heard, machine learning uses a lot of electricity and water, like a lot. Supercomputing, of course, does, but these GPU racks are very resource intensive, and there's even more need to understand performance optimization so that you can choose the right things for the right task. There's a lot of software out there that doesn't optimize the use of GPUs. It's the equivalent of coming home, turning all the lights on, without thinking about what rooms you need to be in. Which, okay, we could argue about light bulbs have gotten more efficient, but this is not the case in the GPU part of the analogy, right? So you really need people who understand kind of the bare metal to the underlying software and internals all the way up the stack. You also need to understand what models to apply. You could run a lot of statistical data science models and get nonsense. There's a whole bunch of stuff that sounds really awesome, but it's made for numerical data. So if you're running it on categorical data, then okay, whatever, I guess you feel good that you used all your credits up or a bunch of electricity. So there's just, things are more complex than ever, and we're going to need people who understand the full stack and all the complexity. And that's, I don't see us moving in the direction to help people be trained for these things, but I think that's one of the next challenges.
Thank you so much. Yeah, would you like to ask your question?
Yeah, thank you for giving me the chance to ask. I think I would I have two questions. One's a bit specific on gateway, and the other is more general. Maybe I start with a short introduction of my background. So I'm a domain scientist on ecology, and currently I'm involved in digital twin infrastructure projects about building digital twin for ecosystem. And in this project, we have two big group of people. One is the domain scientist, including me, who has some modeling background. The others is software engineering, who are really using the developing those virtual research infrastructure. So for me, it's quite heavy, steep learning of all those software engineering terminologies concept. That comes to my first question. I learned another new concept called the science gateway. And if I understand correctly, because it sounds similar based on your explanations, it sounds like what the software engineers in our project says about catalog, saying in a virtual research environment, they try to have a catalog where the researcher can kind of use a search engine for existing tools, models, or data within that virtual research environment to be able to build on, construct their own workflow. So that's, to me, the understanding of a gateway. So it's a kind of a catalog search engine. I just want to confirm if that makes sense or totally wrong. Okay.
I'd say Sandra's the expert here, but I think it's a little bit different. Maybe, I don't know, Sandra, if you want to disambiguate or.
So Science Gateway has different concepts in there. From my understanding, I'm always very generous. I would also think a Science Gateway can be a catalog, but not, Science Gateways are not catalogs. So does that make it clearer? A Science Gateway could be, for example, you go in, it doesn't have a data catalog, but it has, for example, simulation tools. You can start with a button, press of a button, and you get your simulations out of it. You can have a data collection that is integrated into a Science Gateway, but not, as I said, a Science Gateway is then not only a data collection. It has a different aspects. There are different types of Science Gateways. I always think about it, if it's not only a website, but something that, creates, let's say, simulations, that needs an algorithm to search something, that has a big data collection, and you tag it and have metadata and all this. That is a Science Gateway from my point of view.
Okay, thank you.
But there are many different definitions out there, Christine. So
Don't worry, I already experienced that. Thank you for the explanation. I think I understand more. And the second question is a bit more general, but that's really currently the challenge I think it's that challenge I'm facing from domain scientist aspect to be involved in the development of this kind of cyber infrastructure is about the access how do you say? So the cyber infrastructure development require quite a relatively high software engineering knowledge, which most of the domain scientists don't necessarily have. But when I was involved in the process of developing workflow in a virtual research environment, it often comes to the point that I'm realize I don't have the access to to the infrastructure development itself. I'm quite dependent on the software engineers to make any features that I'm desiring, and this kind of is very slowing down the process for development. But on the other hand, I'm also thinking how the mutual collaboration between domain scientists and software engineers should really work together. And is the way correct, like that we domain scientists only act as a user, and how to say, clarify our design, what feature we need, and then it's all up to the software engineers to do that for us. Or it's like we also from the our side, we can have more access. For instance, when we need set up a environment within that infrastructure, configuring all those dependencies, when we over time acquire the knowledge, we should have more access of making change to that infrastructure by ourselves. I'm just curious, the collaboration relationship between software engineers.
Can I jump in on this one, Sandra?
Absolutely.
Yeah, these are great questions, Corinne. And so, yeah, it depends. Yeah, always start a good answer, a complex answer with it depends. But I can give you an example of ecologists that we're working with from our biology department, right? So over the years. So when I say it depends, so we have one ecologist who is an expert specifically in tree health and how that works in an ecosystem, right? And so the ecosystem around it, how it cleans and changes air, et cetera. And he, through his maturity and as a graduate student, wrote all this in Fortran, right? And so we would say, what does it mean? It depends. So how we help him scale his code that is in Fortran, that is a very heavy computational performance requirement, is going to be different. Then we have another ecologist who does more along the lines of quasi-digital twin, agent-based modeling. But these are large numbers, and certainly would prefer this be in Python and a Jupyter Hub notebook. And that requires a different software engineer that we need to align. And theirs is eventually they have this vision where they'll certainly be able to do full ecosystems of lots and lots of different types of agents, right? Animals and plants and et cetera in this ecosystem, and it will become highly performant. But right now, they're just sort of testing on smaller scale, and they can stay in Jupyter, leverage some sort of advanced Python libraries, and it may be sufficient. So I think it depends where that partnership is, on how advanced that team is in terms of and where they want to be. At least in the US and our universities, faculty and researchers have a lot of flexibility. And they can say, look, I'm going to do all my software engineering in-house, and I expect my PhD students to take a bunch of computer science classes in addition to taking this, taking all of their biology classes. Do we think that is the most efficient? Not always, but some would argue that they certainly have a deeper understanding. So I think in terms of where the software engineer, partners and where the domain expert, there's a blur there. And I think at least me, as being a director of a center, we try to meet them where they're at. Right. We try to meet them and understand their needs and their vision. So certainly we try, and our RSEs, our research software engineers, sort of run the gambit from let's try and get the Fortran code performance, as best possible on a large HPC architecture, all the way to, can we get the agent-based model in Python and Jupyter notebooks running on 4 or 5 different cloud platforms? So I think you want to align that where the need is, and I've seen it across the spectrum. But we want to make sure that an RSC can help that domain scientist. that's not a direct answer of exactly where the definition is, but I think, especially in research, we have to try and, adapt. And it's easier for larger centers. We have 15 RSEs at the University of Notre Dame, the Center for Research Computing. So we can, say, okay, someone has this skill set, someone has this skill set. In a smaller organization, they might only have a couple. It's hard to have that software engineer that, speaks all the coding languages, is really DevOps, understands all the architectures. So that can be hard. But I think I would always recommend a domain scientist at least spend an hour, 2 hours brainstorming with whoever in their community is that computational or computer science background to help brainstorm the ideas, to help figure out where that domain scientist. And I know in the US, we certainly have, if your university doesn't have it, we have larger sort of federally funded institutes that can help partner with you, and we can help refer them to those institutes. And I think a number of those, we try to be global partners. And so certainly after this, if you'd like, connections, I'm sure Christine or Sandra and I will try and point you in the right direction to some of those that would be supportive.
Yeah, and maybe if I could just add real quick before we call in Rebecca, I think the Agile software method gives you a lot of good pointers on where these lines can be from client towards developer. And if you're really motivated in the direction of your science, that's a good place to stick. But if you find yourself super excited about the programming side or the architecture side, then come work in an advanced computing center. It's full of people who started as domain scientists who became computer geeks, and there's nothing wrong with that if that's where your passion is.
Okay, thank you so much for the explanation.
Yeah, I wanted to say that is exactly what both of them said. It's there are not defined borders. I think we have in the community everyone from being a let's say researcher with some programming skills to a research software engineer with some understanding of some domains. It's everything in between, so that it is, and that's good so because it keeps it also really innovative. With that, yeah, Rebecca.
Hey, I could come at this with a couple different perspectives. I'll try two. So I'm coming from the natural science perspective, particularly heliophysics. I'm associated with the data repository at NASA, but primarily interested in open science and these kinds of things. But what we're finding from the natural sciences is that we are having some success modularizing the cloud access. So for instance, the 2I2C organization is a nice effort towards having compute that just works and it's already ready to go for the majority of scientists. And there's more complex setups that are possible with those things, and that's where the collaboration with the people behind the scenes, the computer engineers and research software engineers, that's where that takes a step up. HelioCloud is similar to that, and there's even more support for the complex things when people want root command to set up their own things. But we're finding that to be a good approach to support most people and to democratize that cloud access. One thing I wanted to throw at this group, since this is a modeling group, is I've come across this interesting thing called High SDS. I'll put the thing in there, but it's starting to make cloud hybrid, where you can have an on-site system that pulls on cloud resources, like say your high-performance computer runs out of machines. That does happen. And it can pull on cloud resources to integrate that, and then vice versa, where the cloud resources you want to manage cost, but so you pull in your on-premise machines. So I guess my point in even speaking was I'm excited. And this idea of trying to work with the cloud infrastructure and figuring out how to do this, there are groups that are solving these problems. Well, at least significant progress towards. I shouldn't be so prideful as to say solving, but it is exciting progress. And I think we're getting we're getting a good path forward on this, and there's some interesting technologies coming in that are starting to blur on-premise versus cloud. Did I make any sense?
Yeah, definitely.
Okay.
I think I would just say there's so many groups that are having trouble just doing even one or the other, that the idea of the hybrid is rough. But I would say where I've seen the most progress in this regard is in the people who use high throughput computing and groups like the Open Science Grid, who have found ways to queue things that go to either on-prem machines or commercial cloud. I think it's a little more difficult for, you know, HPC, highly parallelized needs, but who am I? I mean, I think this is the way of the future, to be more opportunistic and be more agnostic and create analysis that's more portable. And a gateway can certainly help hide some of that on the back end.
Yeah, I agree. I was going to get the same. I was going to Open Science Grid, and as you're a physicist or talking about physics, Rebecca, we do a lot with high energy physicists in CERN, right? And so they've certainly for a long time been able to sort of federate across a global infrastructure, again, high throughputing, like Christine mentioned. Right. So if it's high throughput and you can really sort of distribute that broadly, there's a lot of interesting things. Data becomes the real challenge. You actually figured out how to like harness all these cores, but are they cores attached to data anywhere that's not saturating a network when you're trying to grab cores in the US and touch data that's sitting on files somewhere in the UK? But yeah, certainly I think there's still a lot of excitement. In some, we talk hybrid to on-prem and to cloud, but I've done a lot with teams over the past 10 years as far as just cloud to cloud, really, because cost and vendor lock-in becomes a concern with a number of folks. Under the hood, ultimately, these cloud platforms, some of them are significantly more expensive than others, depending upon how you leverage the cycles that are available. And so rewriting all of our cloud infrastructure like Terraform, and some of these tools that can take your, bring things up in Terraform commands instead of, specific to AWS or Microsoft Azure or something like that, or Google Cloud. So I think there's a lot of promise. I agree with you in terms of harnessing that. What I have seen in practice with our researchers, as Christine said, any one of those is already challenging enough, right? So just going from laptop to cloud or to on-premise, thinking about, where is my data today? Is it in the cloud, et cetera? And you say, well, we can abstract that. And we can abstract in some regards, but you can't abstract physical components, right? If the network in between those components is really slow, right? You're on-prem in the cloud, there's a latency in that network. And as Christine said, so I can't immediately make a high performance that has an InfiniBand network and all of my processes are talking together in, microseconds, and suddenly attach a little bit somewhere else. Those are the challenges, because the actual physical differences in the equipment that I can abstract. Well, then they get upset that it's running 10 times slower than they thought. I'm like, well, 90% of your cores are really fast, but they're waiting on the 10% that are in the cloud over the low latency network. So there's a lot of interesting things to do there. But if it's fully, one of my colleagues loves to say, embarrassingly parallel, and a lot of the high energy physics have sort of gone that way for high throughput. There's a lot you can do in like global grids, as long as you know where your data is, being, pulled from. So I think there's a lot of promise. I agree.
Yeah, I absolutely also agree. And it's good to look into these things. And I'm happy to hear that you say, oh, we made a really, it goes in the right direction. But I still also think 20 years ago, we talked already about, oh, should we maybe send the data to the computation? We are still working on some similar problems, but we have also much more data nowadays. I mean, it's just really so much more. 20 years ago, we would have not even be able to manage that. So I think all these solutions, you also talk about, are important to get the next steps. And then there will be something again that is like let's say, the explosion of data volume, or what Paul and Christine also talked about, when there's just legacy and more data Our systems are not made for yet, but yeah, happy to hear more about your hybrid system.
Well, it's many people. But I think this group might be well entertained by a talk from the lead of the 2I2C group, James Colliander. If that's of interest, I can send the email.
Absolutely, yeah.
Okay.
Just out of curiosity, how deeply they are into security? That becomes one of our challenges, our biggest challenge for data security in general. Maybe we haven't mentioned this, so maybe it's a good opportunity to mention it, right? So this is becoming more the individual data sets and the intellectual property related to those data sets. As much as we do the open model, sometimes we can make the code open, but the data is not. Or at least maybe it's not temporarily till it publishes. Sometimes it's not as sensitive as, hey, this is intellectual property for a critical investment technology for a startup. But sometimes I don't want the data out until my paper I've had time to validate and this sort of thing, and I need to secure the data in that sort of regards. So we've had an increasing number of focuses on just all the security requirements. And this isn't just, certainly at the University of Notre Dame, there's a lot of US federal sort of regulation around how we do security. And it is one challenge to some of the other smaller cloud providers, is they may not be FedRAMP approved, or they may not be approved for these various. I'm just out of curiosity, do you know how they're addressing that? I know that's for some of the smaller cloud crews, it's hard to get a full security stack team there.
Okay, so hold on, we're over time, Sandra. So
I also wanted to say we are recording this, and if there are things that shouldn't be recorded, I feel like I might
Understood.
want to stop recording at this point.
I don't think I
That's
know anything
fair.
that's secure. So I think I'm free to speak. But I would love to answer the question, Paul, but Sandra, I need to defer to you on timing. Maybe Paul and I could take this offline if that's your desire.
No, so this is like we always reserve 1.5 hours dependent on the discussions.
Okay.
So that you don't have to. It might have looked in the Zoom registration only. Did I put only 1 hour in by accident? Maybe
That's what I throw on my calendar, so I don't know.
So
Do we have time?
so we have another 23
Okay.
minutes time.
Oh,
Yeah.
fun. Okay, then yeah, happy to answer. So couple pieces here. So the thing I mentioned, this 2I2C, they're not in the business of hosting data. They're in the business of creating computational capabilities that are portable between cloud providers and easy for researchers to access. So basically a Jupyter Lab 4 or 5 interface. I forget the version at the moment. But it's a modular compute. They can set it up for you, or you can set it up yourself and at your own institution, and you run with it. But again, they're not in the business of storing data. So coming from a NASA data repository, we're in the business of storing any data that NASA funds. In fact, we're on a directive to do that. The other agencies are moving towards that. So when I say other agencies, I'm talking about NOAA, I'm talking about NSF. NSF is trying an interesting way to work towards their data. NOAA is more operational data being available, so they're trying to navigate how to set that up. But there is an agency-wide effort to, and let me defer to the other agencies. I am not from NASA headquarters, okay? Let me just say that out straight. But there is a wide effort to do open data, and that's US-wide, right? And part of that effort is understanding that these larger data sets, particularly from missions or large efforts, or say the data sets that the ML trainings run on, these things that are just getting too big and too troublesome to download. There is a wide understanding that that needs to be available on the cloud for free. But the idea is to bring the compute to the data instead of moving data around. So if your data lives in Europe, say on their cloud, one of their cloud platforms that they're working on, the idea would be, instead of trying to run your compute from, just going with AWS terms, trying to run your compute from Amazon East or Amazon West on data that's stored in Europe or even Japan, you bring the compute to the data. So that's a vision that's not yet possible. But the concern with data security there is it's all CC0, which means take what you want, do what you want with it, because it's government funded, it's taxpayer funded, it's the community's data anyway. For data that needs security until publication, what I'm telling people, coming as an open science person, we're trying to work that out and figure out what to do, say, with data repositories, which is part of my job right now. The idea so far is we're playing with the idea of having Zenodo. Let's say there's a NASA version of not NASA version, like a NASA, I think the word is community, a NASA community on Zenodo, and every data repository has their own collection. Zenodo has the option to keep it private for now and then make it public at a later date. Same thing with the Open Science Framework. Whether it's a data set on there, whether it's a registration, it can be private for now and then public later. And that works with the publication idea. But when you have data sets that have, say, ITAR or personally identifiable, if I can get my terms straight, PII, so acronyms, data that's a concern for security that certain countries shouldn't have and others should, then that's out of my league. As my boss would say, that's above my pay grade. Go to headquarters and talk to them. But that is a question that they're talking about. That is a question that the data repositories have. And basically that requires authentication. The way that occurs on the cloud is not within my knowledge. Did I get the ideas across? Did I answer the main points?
Yeah, I think that was great. Thanks. Yeah, I
Okay.
think any of the data I pass back to Christine. She's our national data expert on all these. As she mentioned, she's on enough global panels to, if she had any thoughts, I will pass on that one. But yeah, it makes sense.
It's complicated, I guess I would say. There's a lot of approaches. Let's see, I'm trying to think of what we could unbundle while we're here together. Maybe it's just the concept that it's helpful to have the metadata exposed even if you can't expose the data.
Yes.
And so maybe that's a place to start. And
Sorry,
let
I
people
wasn't
know.
muted.
No, that's good. I'm glad for the enthusiasm. And let people know, okay, there's more here, but you're going to have to go through a process and not kill yourself trying to figure out how do you get the maximum amount of data into the open if it's just not possible. But exposing those metadata records. And so there's a variety of ways to do that. Zenodo is an awesome place. I've deposited a lot of stuff there, but it's a generalist repository and it has restrictions. By the way, there's a great review out, I think just in the last month. I think the lead author, Shelley Stahl, who's from the American Geophysical Union, that compares generalist repositories and outlines like, here's the size limitation on files from Zenodo, versus Figshare, and 3 or 4 others. And once I stop talking, I'll try and find the link to put it in the chat. I would say place data where your primary audience is going to look for it. Often that can be in a domain repository, but barring that, putting it in your institutional repositories also can be helpful. They have a stake in keeping your data preserved and being a good steward of it. We're really lucky at the San Diego Supercomputer Center. We're part of UC San Diego, and we have a great research library that, that's where my primary generalist places I use. I know I could just go on about these topics forever, but maybe I'll stop there. And yeah, when you get into things that are export control or have PII, you really have to deal with the regulations for that particular data and come up with a solution that's possible. But again, I love the idea of publishing metadata and let people visit what's possible.
Thank you so much. And we have another question.
Yeah, thank you, Sandra. Since the discussion was on data, in this project we also have one of the pillar is about data verification. To that I also have a question similarly. when we saw the discussion was on data accessibility, but to make the data interoperable with the infrastructure. We also have we also are working on verify the data, so to follow some certain type of standard, and then there I run also into the problem like to make data fair. It sounds like a technical task, but then you also need people who really know what the data means to really do the data thing. Then it becomes very difficult to collaborate between the scientists who know the data and the people who have the technical skills. Yeah. And that's similar as what I asked about the collaboration. I don't know whether you have any experience or thoughts to share. Thank you.
Yeah, I spend a lot of waking hours on the issues you just described. So the FAIR principles that have been out now for 10 years, because they had the workshop 2 years before they published the paper, which can make us all feel good about how long these things take to get into published format. They were meant to be general and to outlive any specific technology. So the implementation's left up to interpretation, and it differs from domain to domain. And then it really requires people who are pretty literate in research data management concepts, but also have knowledge of the data as well. It's just not an easy problem. You have FAIR validators out there, but most of them are really, and I don't want to insult people who made great things that I couldn't have made, but a lot of them are toys more than they're really helpful validators. And that's because there's an infinite number of ways you can architect data, but validators don't have a great way to anticipate what these are. And let me explain. I think the best FAIR evaluator out right now is Fuji, which is F-UJI, and I forget what it stands for, but FAIR something. And if your repository that you're pointing it at or your data sets are not file-based and don't have DOIs as the persistent identifiers, then everything fails. But you could have a repository or a data collection that was perfectly compliant with FAIR principles that fails Fuji. And so I think that just really exposes how complicated it is. And so unfortunately, at the moment, you really do need to work with data stewards or have people on the project that have been trained in these concepts to really take full advantage of this framework. But once you do, it's extremely powerful. And I think this is how we're going to unlock some of the most interesting answers to some of our hardest problems in this data that we have that you can't currently, use between different experts.
Before we go to Rebecca, Paul, you also would like to say something about the topic?
No, I think Christine did great on that one.
Okay. Rebecca?
Hey, we have to be best buds or something.
I was thinking the same thing.
So I'm going to come at this from a different perspective. So understanding that we have a spectrum of data here. So at NASA and in any research environment, we have the data sets that get funded by proposals to be used by the wide community. At the other end of the spectrum, we have data sets basically supporting publications. Like, I created this data set through this processing stage, and here's my script that made it. Here's the data set at the end of it. It's not, hopefully don't do numpy.save. You'll be on my bad side for the day. Here's the data set supporting the publication and those kinds of things. So you can do the same. Okay. You can take the FAIR principles, and at one end of the spectrum, you have this asymptote that's impossible to make a data set completely fair. There's always going to be something that somebody doesn't understand or at the other end, something somebody doesn't care to read, they screw up, they published based on your data set, they use it completely wrong, so on and so forth. And you're like, I am aghast. I keep hearing these stories, and I'm like, this is why we have reviews. Participate in being a reviewer. I can't help you. But we can't demand the asymptote for every data set that we produce. It's too much of a burden on the researchers. They're stretched hard enough to just publish their papers. So there's some sort of minimum that we need for FAIR, and there's some sort of ideal or something around the ideal we want from the NASA perspective, mission data, from other agencies, our observatories that produce data that we all depend on. We want that to be the best that we can, even building software tools on front of it, even building quick look tools, so on and so forth, the things data repositories do. But the sanity I'm trying to inject into this FAIR conversations that I'm hearing is that we can't demand the rainbows from everybody. We need to find the ground and demand that. So demanding enough metadata to cite the thing, plus maybe 3 little things. Like if you add descriptions, then you're suddenly compatible with schema.org, and you can add website tags to your data set, to your data set's landing page. If you add some keywords, that makes it more searchable. You'll get more hits on your page, right? So this is the same thing you do for your publications. They require you to pick 3 or something like that. Same thing. Your data is just as important in your publication. Your script is also important too. So I did a poster on this. If anyone cares to see it, I'm not going to post it in the chat unless someone says they're interested, because I try not to be that kind of person. But there has to be some sort of
Put it in the chat.
okay, I'll do that in a second. But we can't demand rainbows from everybody because we have other things we have to do. We're not paid. Most researchers are not paid to create metadata. So there, trying to inject sanity into the conversation. I'll track down that link.
Yeah, well, and what Sandra said, I really look forward to checking out your poster. And I don't want to monopolize things, Paul. I'll just throw in a couple ideas here. So you're absolutely right, Rebecca. I really urge people to think in terms of FAIR, not as binary, like you're fair or you're not. Think of it as good, better, best. To say it in a more exacting way, I work a lot in terms of FAIR maturity models. Like here's like kind of a minimum you could do. Here's moving the needle. And if you had enough resources, here's nirvana. We use this concept in EarthCube, which was a $85 million portfolio of projects from the National Science Foundation. I headed the last coordination office before the program closed. And we came up with this thing called recommended standards and specifications. And it focuses both on data and software. But I think what's most interesting is we tried to employ this model where we had minimum product specifications, ideal, and then what we called next level. Not everybody's going to get to that last level, but I think it's too daunting if, like you said, you're always thinking in terms of rainbows or the most perfect, because yeah, certainly a key NASA data set that comes off some $1 billion mission, that should be, someone should curate the hell out of it. It should be perfect, right? But the rest of us, we have to do what we can. I also want to bring up something we haven't talked too much on, although the C2I2, if I got that right, those people are all about this. And it's the idea of the living paper through a notebook. So Yolanda Gill wrote this, she's at USC, she wrote this great paper, I think, a little less than 10 years ago, about a vision for how we should publish. And we tried to start this a bit in EarthCube. Actually, we went to the Jupiter people and they said, yeah, we want to run notebook competitions peer reviewed, but we haven't yet. So we started it in the earth sciences. And you can go to earthcube.org and we have a directory of curated notebooks that went through a peer review process. I think the really fun thing is that it gives especially people who are taking part in the research process a way to publish their work product, but it hits at reproducibility, about all the things that we've talked about. And this work has been continued by AGU and funded by the Sloan Foundation. They have a project called Notebooks Now that carries on, and they're actually, I think, and I'm not the spokesperson for this, but they are working with one of the journals within AGU's portfolio of journals to implement the ability to take in a notebook as a paper.
That's the Nature Journal, right?
That's where I'm out of my depth on which one, but we
Okay.
certainly, Sandra and I work closely with the people working on this project. If and maybe that'd be a good future topic to get a check-in from them on what they're up to.
'Cause I'm interested in doing one of those special issues with that kind of thing, but I don't think my community is quite ready for that. Maybe next year.
So actually another project I'm part of, which is a data catalog, bringing it back to something that Quinn raised earlier in the call. We have been working on a paper, which is we have a grant, a CSSI software grant through NSF, where we thought we'd run some more of these notebook competitions with different earth science communities. And we found there's a lot of impediments. And so we're working on a paper about notebook competition readiness, if you will. That's not our fancy title, but that's the topic of what elements need to be in place for a community to be able to do something like this, and how do you skill up?
Interested. I want that.
USRC also does look into these things. We have notebooks submissions for our conference. We had the first one last year. This year, yeah, happy to, discuss that topic longer. We have 4 minutes left from the official time. So I always block 2 hours, but I'm also respectful of everyone's time here. So with that, if people still would like to continue the discussion, or otherwise reach out to us. We have each other's emails. Yeah, join the community. There are a couple of things also, for example, regarding to fair, and just to make it as fair as possible. So we have developed some guidelines for science gateways and virtual research environments, and where it's really like, this is a minimal, like Christine described it, where researchers can get the help, that it's like, oh, if you do these 3 things in your virtual research environment, you're fine. You did the first step. All is good. So we are working on things like that. This is a working group in RDA. We are working on with that one.
Sandra, there was one more just as we're wrapping up. We didn't touch on it significantly, but I think, for all of the, benefits of fair and reproducible, there's a huge opportunity, right, to tag along with the momentum around machine learning and, AI, ML. I'm sure, no surprise, I'm sure that's dictating a lot of Christine's time, but certainly for responsible AI and trusted AI, right, especially as we've sort of gone into this, frenzy of large language models, that the underlying data is critical as we build these out, and having good ontologically based knowledge bases and metadata on that particular data is how we're going to get to not only get to trust and get to responsible, to build better, more accurate models. So I think there's an opportunity to align a lot of these fair data principles with the needs of trusted AI, right, with the needs of responsible AI. And I think there's going to be a lot of work. We're part of the AI Alliance. There's a whole trusted foundational models deep into ontologies and data curation and this sort of thing. And I certainly see that only growing in the amount of interest across, globally and in the federal government and trusted AI. And all of that comes back down to a lot of these great, data practices and data curation. So, I think this is, only going to be an area that's going to be, critically important as we develop more sophisticated sort of agents on top of these AI platforms. So we haven't talked deeply. A lot of what we talked about was reproducible science, and we've talked about notebooks and simulations and software stacks. And I think when it comes down to the models around the data, all of the momentum around trusted and responsible AI and large language models comes back to good data practices.
Absolutely. Thank you so much, Paul. Thank you so much, Christine, and everyone else joining for the call. this is very exciting discussions. I really like that. We will copy everything also from the Zoom chat. Ishmael, yeah. So, and as I said, we will develop a paper. We will write on a paper who wants to contribute to it. It's invited. And we will have our next workshop. And now Ishmael, do you have it? Maybe the date directly? Sorry, I don't have
May
it.
3rd of May and 24th of May, but if I've got this right, yeah, I can share my screen.
Cool.
That's everything we have lined up and everything from before. I'll give it back to you, Sandra. Thank you.
Thank you. So yeah, you see my thread is about sustainability. And then we will talk May 24 about assessment.